Suppose you want to derive the following formula: P and not P, and the whole thing negated. So this is an instance of the so-called principle of non-contradiction. And this principle says that it is not the case, so this is one negation, it is not the case that you have P and at the same time not P. So it's not possible to say P and not P. It's not possible to say I'm walking on the grass and I'm not walking on the grass. That the conjunction of one statement and its negation is not possible. So that's what the principle of non-contradiction says for any possible statement P. So how are you going to derive such a thing? And the method is always going backwards. So we want to create a derivation that at the bottom, so I'm going to write it here at the bottom has this formula here. So we need to arrive at the point where we have not P and not P. An important thing to note here is that we have this symbol, this connective, which is the negation. And in our system of derivations, we handle negations in the following way. We use the notational convention. And the notational convention tells us that whenever we have a negation, that negation is equivalent to the negated formula implies the contradiction. So if I have a negated formula, let's say not A, where A stands for any possible formula that I have, for example, not P, then this is the same as A implies the contradiction. This symbol here, this perpendicular symbol. So that means that every time I see a negation, I can simply replace it. So every time I see something like this, I can simply replace it with that, just because of the notational convention. And so we can do something like that here. So I'm going to write here a notational convention, so NC, and above the line, I'm going to translate not A in A implies the contradiction. Now, our A in this case is this whole formula here. So I can translate not A into A implies the contradiction. So this means that I can write P and not P implies the contradiction. So you see, I took my not A and I made it into A implies the contradiction. So this is just because of the notational convention. And you can go either way. So this is equivalent to this and this is equivalent to this. So they're kind of interchangeable. There's no difference between the two. That's the notational convention. Now we are at this point, and you'll recognize that this is an implication. Has an antecedent, P and not P, whatever is on the left-hand side of the implication, and then as a consequent, this symbol of the contradiction on the right-hand side of the implication. So whenever I want to derive an implication, what I need to do is to assume the antecedent. So I'm going to assume the antecedent somewhere up here. So P and not P, and call that assumption 1. And then try to derive the consequent, which is this contradiction symbol here. So I'm going to write above contradiction. So the goal here is to get from this to this, and I can then write this P and not P implies a contradiction because of implication introduction. So remember, the rule of implication introduction says, so I'm going to write it right here. So if you assume some formula A, and then you go through various steps in the derivation and you get B, then you can write A implies B because of implication introduction. And then you can cancel your assumption because you have incorporated as an antecedent of your implication. So that's what we're doing here. Now the question here is, I have this assumption number one, how do I get to the contradiction? What's interesting is that this assumption here is effectively a contradiction because it contains P and not P. So I just need to unpack this a little bit in order to get to my contradiction. So one thing I can do here is I can extract from this not P. And these I do just by conjunction elimination. I'm just taking one of the two components in this P and not P. Now at this point I can apply my notational convention that says that not A is the same as A implies the contradiction. So I just use my notational convention and C, and I just say P implies the contradiction. All right, so I'm at this point, how can I get to the contradiction here? I have P implies not P. All I need to do is to have, let's say P here, and then by having P implies the contradiction and then having P by implication elimination, by the rule of implication elimination, because it's like I had A implies B, A therefore B. Here I have P implies the contradiction, P therefore the contradiction. So now the question is, how do I get this P? I cannot just simply assume P like that. That would be wrong. How do I get this P? Well, that's easy because I can assume P and not P. That would be the same as my assumption 1 up here. I can repeat the very same assumption as many times as I want. I call it with the same name. And here I'm going to use conjunction elimination, and instead of taking out not P, which is what I did here, I take out P. And so now I have my P. I haven't assumed anything I was not allowed to assume, and I had the same assumption here. I can go through all the steps. Can I cancel this assumption? So I can assume everything I want, of course, but I always have to make sure that I cancel my assumption. So I need to check that I should be able to cancel this assumption here, which I've repeated twice. And I can indeed cancel it. I can cancel it when I apply the rule of implication introduction. Because look what I did. I assumed P and not P. I went through various steps and I got to the contradiction. So that allows me to put P and not P as the antecedent and then put the contradiction as the consequent. And so this allows me to cancel my assumption. And so now I have a derivation of not P and not P. All my assumptions are cancelled, and therefore I'm